Today we'll see what we can learn from galaxy observations using the relativistic Doppler shift. Astronomers can study a galaxy through the light it emits. Astronomers will often split the light from a galaxy into its constituent wavelengths and then plot the resulting brightness versus the wavelength on a plot called the spectrum. Now, dark lines in this spectrum correspond to the gas, so the light passing through a cold, dilute gas that absorbs at characteristic wavelengths. So we would call that, the dark lines in a spectrum, an absorption spectrum. And we can learn a lot from studying the absorption spectra of galaxies. Okay, so say we know the wavelength of an absorption line coming from a galaxy that would be stationary to us. So since the wavelength in the frame where the galaxy is stationary relative to us is the same as the wavelength in the source's rest frame, we'll call that lambda s for source. However, say we observe a different wavelength, lambda observed, than lambda source. This means that the galaxy was actually moving relative to us. And these are related by the relativistic Doppler shift formula, which I've written here, where beta is v over c, for v the relative velocity. Now, we've defined the conventions here so that beta, or equivalently v, is positive for the galaxy approaching us, so for the source of the light approaching us, and negative for the source of the light receding from us. But we would plug in negative beta here for a galaxy that was receding from us. Now, say that we measured a wavelength, lambda observed, that was shifted towards longer wavelengths than we would have expected. So lambda observed greater than lambda source. This we would call a redshift, since the shift is towards the red end of the spectrum. Alternatively, say we observed a wavelength that was less than what we would have expected for a stationary galaxy. So a wavelength shifted towards shorter wavelengths, the blue end of the spectrum, is called a blue shift. Let's explore this effect in a problem. How fast and in what direction must galaxy A be moving if an absorption line found at 550 nanometers for a stationary galaxy is shifted to 450 nanometers for A? How fast and in what direction is galaxy B moving if it shows the same line shifted 700 nanometers? We're given that lambda source for A is 550 nanometers, and lambda observed for A is 450 nanometers. So since lambda observed is less than lambda source, we would conclude that the observation of this absorption line constitutes a blue shift. Alternatively, we're given the lambda source for galaxy B is also 550 nanometers, but lambda observed is shifted towards longer wavelengths, 700 nanometers. So this observation constitutes a redshift. Now we can figure out whether these galaxies are coming towards us or away from us and the velocities at which they're doing so by solving for beta in our relativistic Doppler shift formula. So remember, beta is equivalent to solving for the velocity. Beta equals v over c. So just squaring both sides of this equation and moving things around, see the attached PDF for more details. What I'd find is that beta equals lambda source squared minus lambda observed squared over lambda source squared plus lambda observed squared. Okay, so remember that for the sign conventions in this formula, we said that the velocity was positive if the galaxy was coming towards us, whereas it was negative if it was receding from us. So this was positive velocity for it coming towards us. Therefore, when beta is positive, or when lambda source is bigger than lambda observed, the galaxy is coming towards us. And this is the case for the blue shift. So for galaxy A, which is blue shifted, beta, or the velocity, the relative velocity, is greater than 0, and we can conclude it's coming towards us. The velocity at which it's coming towards us is given by plugging these wavelengths into our formula for beta, and doing so, we would find that the velocity is plus 0.20c. Meanwhile, if lambda observed is less than lambda source, then beta is negative, and we would conclude the galaxy is receding from us, which is the case for the redshift. So for the redshift, beta is less than 0, and the galaxy is receding, and galaxy B is receding from us. Then plugging in these wavelengths into our formula for beta, we would find velocity of minus, so away from us, 0.24c. Astronomers have used measurements of the recession velocities of galaxies to determine that the universe is actually expanding. Like 2 points on a balloon being blown up, distances between objects in the universe are actually increasing. Further, observations of redshifts of supernovae less than 20 years ago, 2-hour shock, taught us that the expansion of the universe is actually accelerating. The rate at which the universe is expanding is actually increasing.